Hello and welcome to this applied ergonomics lecture 21. We were in the last lecture trying to do a case study regarding two different positions of lifting, that is the stoop lifting or the squat lifting. And in context of that, we had looked at how biomechanically we could actually classify these two techniques as more convenient or less convenient. And the objective here was to assess the biomechanical evidence in support of advocating the squat lifting technique as an administrative control to prevent lower back pain. So, these were the two different postures, and we basically advocated that in the squat lifting technique there may be a lesser possibility of damage to the musculotendinous structure which the human body would have. And if I looked at the two different load points, we can see that in this particular hip joint area there is a almost a 100 lb 100 pounds load while lifting a 10 pound, which is not a very good situation, particularly for the stoop lifting, whereas in the squat lifting 10 lb or a 10 pound load means actually 10 pound load on the musculotendinous structure as well as the structure of the spinal joints. So, basically if we looked closely at how you can categorize these joints biologically, so you will have the basic spinal structure which contains the ligaments, the invertebral disc, the vertebrae, so on and so forth. Then there are these musculotendinous structures which are responsible for creating all the active components and the forces between these joints, so that they are able to rotate with respect to each other and move with respect to each other. So, there are components like muscles, musculotendinous junctions, tendinous insertions, so on and so forth, and the type of forces that such joints do produce are compression forces, shear forces, tensile forces, stresses and muscular forces. And these are some defects which are shown here. For example, what can shear do in terms of damaging the spinal structures, or what can compression and subsequent compression fractures do for overall joint strengths, etc., is illustrated in this particular schematic. So, what this study indicates is that you have different techniques through which you can gauge such forces. Some of them are through measurement of, let us say, the intraspinal pressure or even like the intramuscular pressure. And what this study basically is about, that you list such techniques and then on the other hand list these different compression forces, shear forces, tensile strengths, stresses, and try to evaluate which technique would be suitable for measuring what kind of force in the spinal structures. So, basically this is a sort of a you can say a parameter of the back load, and their indicators derived from direct measurements or maybe even some model calculations sometimes evaluated for use in comparative studies of both the lifting techniques, that is the squat technique as well as the stoops technique. So, it so happens that some measurements are possible through either measuring the IDP, which is the intradiscal pressure in the spinal area, or the intra-abdominal pressure, this is in the abdominal muscles. Okay, then there are electromyography plots and linear swell meters. These are different techniques for measuring the force indicators, whether they are muscular compression forces or shear or bending moment or ligament stresses in the spinal region, or even there are certain instead of measured indicators, there are also some model based estimates which would give you an idea about the muscular force and the compression plus shear or the bending moment in different bony part, okay, of the system subsystem. And there are different indicators which are either the measurement technique or a particular model through which you can get such forces and shear in stresses. And so, for example, in the muscular force category, the compression can be measured through physically through either electromyography or measuring the intradiscal pressure or even measuring the intra-abdominal pressure. And what has been done as a study is that there are certain methods which are deployed to obtain these measurements, these muscular force compression measurements. For example, the surface EMG can be used in case of measuring the muscular force compression, and although the data that is indicated from the surface as a function of the depth in the muscles has relatively low validity to probe what happens within the muscle. So, there is a indicator which has been rated now, and so if you look at, if the indicators do not have sufficient validity, you give a score of 0. If the indicators have a limited validity, you give a score of 1, and then a 2 when it is sufficiently validated, or if it is a highly validated indicator that this would indicate whether there is a higher amount of compression force or shear stress. So, that such indicators are rated number 3. Okay, so, in the same manner, these indicators, these different techniques are rated with respect to the measurement here of the different forces like the compression force or bending moment, ligament stresses, so on and so forth. And some of them have low validity, some of them have very high indicator. For example, this IDP measurement, which is actually invasive, where you place a pressure transducer inside the region of the disc which you want to measure actually. So, the intradiscal pressure is directly coming as a consequence of whatever is being felt by the pressure density transducer at that level. So, this has a relatively high level of validity. So, every time this reports the right data of the IDP or the muscle force compression. Similarly, there is this radio pill catheter which is used for the abdominal pressure, but it has relatively lower validity towards ascertaining what is the muscle force compression in the spinal region. So, there is some inconsistency that the abdominal pressure increase means spinal pressure increase. So, it may not be always necessary. And then there is also a stadiometry technique which observes the shrinkage. Shrinkage is the indicator measured through this, which has an evaluation rating of about 1. So, such things have also been done for the model estimates, and from these evaluation mechanisms there are certain critical believers which would be needed to understand more appropriately what are the muscular compression forces. And so, taking the high indicators, you could actually now do an analysis regarding the stoop or a squat system, and there are certain results which come in line with this when you subject the whole human system to different variables, like let us say different forces of compression or bending moments, different distances across which you can move the musculotendinous structure, or at different velocities in which you move the musculotendinous structure to execute motions in both the lifting techniques. And so, the results indicate that the majority of the studies, namely 5 studies made in this paper, predict substantial reduction about 10 to 34% in the back load when using the squat technique as opposed to the stoop technique. Okay, in at least one of the experimental conditions in which such measurements have been done. And you have to understand that these are being studied on the basis of only the high indicators, where the indicator refers to exactly the level at which accuracy or precision can be obtained for physical measurements or even modeling related predictions. About 13 studies conducted in which the net moment or extensor moments are individual joint moments. Net moment is when all these joint moments take place, what is going to be the net moment of the whole system. They were estimated using some dynamic analysis technique, some modeling technique, and they found that the backloads in 2 techniques to be either significantly higher in squat lifting, 4 to 18% namely, particularly when we are talking about the net moment, but the extensor moment, which is only a local phenomena around a joint. Let us say there is a joint and the joint exerts certain amount of moment which performs the bending about that joint. So, that is not significantly different. Okay. So, although the net moment basically becomes different, so therefore, the levels in which the extensorial moments change between one joint to other, they are much higher in this particular case. So, one of them of course reported a substantially lower, about 13% net moment in the squat lifting case. So, certainly through these studies using techniques of measurements or models which are high indicators of the compression pressure or the bending moments within the intraspinal region or the musculotendinous structure associated with the intraspinal region, one can predict very easily that in all the cases squat lifting happens to have a better performance in terms of giving lesser loads, okay, to the whole structure in comparison to the stoop lifting. So, it is a sort of a conclusive evidence, a study that how these 2 lifting techniques are different. So, one can do such kind of probing studies so to ascertain whether one is better than the other, to get a gauge of really what is the internal anatomical pressure behavior between 2 different positions, 2 different let us say ergonomically designed activities, and based on that you have some evidence, okay, that one is better over the other. So such positions which are considered to be better are normally useful for the purpose of ergonomic design of any activity, which we will probably cover in one of the later sections while designing seating arrangements, etc. Such kind of pressure differentials, such kind of measurements, and sometimes of models also are really needed for checking what position is better or what position is not better, for example, for people using different such orientations. So now we will look at little more about the joint anatomy and the basics of biomechanics, that how with respect to different joints, this all rotation, translation, let us say rolling action between the different areas of the joint, they can sever, okay, as one executes different motions by his limbs, his or her limbs with the body. So if we look at fundamentally to the basic principles, we already know that mechanics is really related to the study of forces and their effects, and kinematics deals with the geometry of motion of the objects, particularly the displacement, the velocity, the acceleration of members moving with respect to each other, and this is typically done without considering the forces, okay, or taking into account the forces. So that is primarily how kinematics is defined. So is kinema, the motion related effects, and then there is yet another kinetics, which is the relationship between the force system acting on a body and its effect on the motion of the body, and basically biomechanics, which I have earlier defined as the application of all the mechanical laws, particularly to living structures, so specifically to the locomotor system of the human body. So it defines, for example, interrelation between the skeleton muscles and joints. It also considers bones to play a leverage role. I will come shortly to it, how a fulcrum and a lever can be associated with different joints. It also helps in ascertaining ligaments as hinges which would provide interaction between let us say two different components of bone members, which is having a relative sliding with respect to each other, and then there are muscles which would typically be the locomotor, the one which provides forces for doing such action. So the knowledge of joint mechanics therefore is very, very important for sometimes the just for chiropractic adjustments, which is about alternative medicine concerned with diagnosis and treatment of unverified mechanical disorders of the musculoskeletal system, especially the spine, okay. So if you could know that some displacement has occurred or some deviation has occurred from the routine structure, which is creating a sensation of pain, how you could actually reorient back into the normal orientation by giving it motion in the opposite direction, okay. So which are about all these adjustments that we are talking in this particular slide. So if you need to really do this, if you need to understand both the kinematics as well as the mechanics of all these components, the bones, the ligaments, the muscles, to give a high degree of interrelation knowledge of motion between these components. So if we looked at again fundamentally how the musculoskeletal structure is going to result in different leverages. So we first need to again look at what is a lever. So for example, here there is a rigid bar, it is pivoted about a fixed point, which is also known as a fulcrum, okay, and there is a force applied on one side which results in some kind of a force into force arm, and there is a balance of moment about this particular point of fulcrum, which is able to, by using a greater arm, lift off a much higher resistance or a load. So this is one of the simplest machines that one can think of, and basically when we talk about body parts like the limbs or even the spinal region, etc., they are all subjected to lifting off loads, etc., through what we know as the leverage action. So muscles apply the forces. For example, let us say we talk about this particular orientation of the hand when we are trying to lift something. So obviously the upper portion of the hand right here is able to give a force which is going to be able to lift the lever arm. So whatever force is generated in this region you can think of this as the fulcrum point, okay, because we do not change the orientation of this, it is fixed with respect to the shoulder. So, if this is the fulcrum point, I could generate a load which would be able to, about the fulcrum point with a greater arm, be able to lift a load which is probably higher in comparison to the muscular force that this part of the hand, the upper arm, is giving onto the fulcrum. So, this is given here, okay. So, this is in a way a sort of a lever, you can say, lever of the first principles. So, it is a class 1. So, again there is a class 2 where the resistance in between the axis resistance is in between the axis and the force. So, this is the fulcrum point in such cases, okay, and the resistance that you are wanting to lift is actually around this. So, you have to begin categorize different motions within the body where this is possible, and there is a force on the other side which is able to lift up, okay, the load which is placed in between the fulcrum and the load fulcrum and the force. Similarly, there is again a third category where the force is in between the axis and the resistance. For example, in this case the force that you are providing by this arm is about this fulcrum point which is being given by this other arm of the particular body, and it is able to lift the resistance. So, the force comes in between the resistance and the fulcrum point. So, these are the different orientations in which you can use the limbs so that they can have different principles of lever and leverage action. So, every movable bone acts alone or in combination, forcing a network of lever systems, usually of all these different classes that you saw in the last slide, the first to third class. And there are no second class levers in the body except human mouth. There is only 1 or 2 regions where in the mouth where you could actually have second, otherwise first and third are utilized almost always within the limbs. So, third class lever system in human body is, for example, flexion of elbow joints through contraction of bicep muscles, and similarly first class lever system could be extension of the elbow through the contraction of the tricep muscles. So, these are some basic ideas of how you can either flex or extend, okay, muscular system, creating different positions of fulcrum point with respect to the force and the resistance. You can see the force here is in this direction, this is the fulcrum point, this is the resistive point. Similarly, the force is in the other direction altogether, and there is a fulcrum point here which is leading in a resistance in the other direction, okay. So, something like you can say, in one case you are lifting or flexing, another case you are trying to extend, you are extending, okay. So, extensional. So, this is the first class system, and the second the third class system is basically flexion of the elbow joint. So, this is how you understand joint mechanics. We would also like to organize a reference coordinate system for the body to give shape to. So, for example, there are different body planes across which you could see what is going on in terms of muscular movement or movement of the musculoskeleton structure. So, there is a mid sagittal plane. For example, if this I am, let us say, the concerned person through which this analysis is being done. So, the mid sagittal plane really would be something which will divide the body from top to bottom into half and half, okay. So, this particular plane right here, for example, is the mid sagittal plane. There is also a coronal plane. Coronal plane is actually parallel to the human body. So, if it cuts the body, for example, from here all the way to the legs in the center region of the body, with the body being in the same plane as the plane itself, so it is called a coronal plane. And then there is a transverse plane yet, which is actually going to divide the upper portion of the body from the lower portion. So, this actually is a transverse plane. So, we have different plane windows through which you could categorize, and now all the motions which take place are with respect to the axes across such planes which are formulated. So, the mid sagittal plane divides body into right and left halves, the coronal plane divides the body into anterior posterior, and the transverse plane divides the structure into upper and lower half components. So, this we must understand before going ahead. So, what we did is that we studied what are the basic principles in terms of kinematics. We also studied some of the concepts related to lever. We also studied some of the concepts where we could see how body planes are categorized to just coordinate them in a proper manner and organize to have some, let us say, numerical values associated with the positions like rotation or translation, etc. And then we start studying axis of movements. So, when we talk about axis of movements, the significance of defining this coordinate system is in defining the extent of the types of movements possible at each joint of the body. So, the picture on the right for example shows such a coordinate system. So, you have the x, y and z coordinate based on all these three planes intersecting with respect to each other which talks about how these joints are positioned with respect to each other so that they can move relatively in a certain direction following some sign convention. That movement could be either translational or rotational at different places. So, it is somehow to define that structure of axes through which all the movements can be suitably studied, just as you do in kinematics, the study of links or linkages or members. So, the picture on the right shows coordinate systems, and x axis is basically the coronal axis, lies in the coronal plane. Similarly, the y axis, as one can see, this is the portion of the spine that is being shown here, at least the bony portion of the spine. So, the y and the z axis correspond to the mid sagittal plane and the transverse plane. Okay, so that is how the axes of motion or movement are defined. So, let us now start talking about the joint motion with respect to all these different axes. So, let us study joint motion. So, the basic motions that we would be concerned about here is mostly flexion and extension, and if this particular subject here is bending forward for example, and so this forward bending is in a way a rotation in the mid sagittal plane, okay, around the x axis, so or the coronal axis. So, this is called the forward flexion. So, similarly if you try to bend backwards, the whole pressure will be shifted from your spine to, let us say, the toes, the ankle, the toes, the foot, the ankle, and then of course all the way to the hip joint. So, that kind of a backward motion is also a flexion towards the posterior. So, all such flexion motions are considered to be rotations about the coronal axis in the sagittal plane. And similarly, if we talk about extension, extension is just the motion opposite to the flexion. So, whichever side is extending is basically providing the extension, okay, in the structure, the bone structure. Similarly, I could do the same by lateral flexion. For example, if I bent more on the right side or the left side, for example, this is a right bending I am doing, and then this is the left bending. So, essentially what I am trying to do is to move or rotate the the spinal system in the coronal plane now with along the x axis. Okay. So, this is again something which we know as the lateral flexion. Similarly, if I wanted to move my arms around, and let us say if I wanted to either do an abduction where the arm goes from normal position all the way to let us say shoulder height, and then back from the shoulder height back to the normal position, which is called adduction. So, all these motions including the lateral flexion as well as abduction and adduction can be considered to be across the the coronal plane along the x axis. Okay. So, in this manner you are trying to categorize the different movements in terms of forward motion, backward motion, side motion, and fitting the axis system that you have developed in the last slide as I talked about to such motions. Okay. So, that is how you can study joint motions in a organized manner. You can see for example here there is this medial and lateral rotation of the extremities, the rotation of the spine occurring about the transverse plane. So, if I wanted to bend let us say for example the body, so without standing in the same position, if I want to bend the body to the left or the right, what I am essentially doing is across the transverse plane which separates the lower portion of the body from the higher portion, I am trying to execute a rotation again along the x axis, but the rotation is taking place along the transverse plane. So, you have learned that how forward bending, reverse bending, side motions, and let us say motion of the upper portion with respect to the lower portion are along typically the sagittarial plane, the mid sagittarial plane, the coronal plane as well as the transverse plane. So, this is again an organized way in which you could record all these movements with respect to each other. You can also talk about translation movements, particularly translation movements related to the joints. You see, this is how the structure of the spine actually would look like, and so in some cases there is a possibility that there is a posterior to anterior glide of one of the components. In fact, this is actually a defect which happens in the spinal system due to injury etc., which is also known as enterolisthesis. So, what would happen is that one slide or one section of the bone of let us say the spinal cage would slide towards the the anterior side or the front side from the posterior side. Okay, so basically let us say something where this thing slides in front over the other bone which is below it. Okay, and similarly the other way, the retrolisthesis is for the anterior to posterior, there is a gliding action of one bone with respect to the other. So these are some defects which can be caused, or even there is during the flexion or the, let us say, extension, there are these kind of small phenomena. Only if the extent of motion is beyond a certain level which is beyond repair, then we call it a disc slip. Okay, otherwise we can consider that to be routine or normal. Similarly, there is lateral to medial glide or medial to lateral glide, which is also known as lateralisthesis, which is again translating along the y axis of motion. So just look into how I had categorized before and try to figure this out. So there is also curvilinear motion, which is actually a combination of all the rotations as well as translations, and this is typically the most common motion produced by the joints of the body. You have to remember there are tendons and there are muscles and ligaments which are present all round, and so they are enabled, the human body is really enabled to handle such curvilinear motions with combinations of rotation and translation to a certain extent. But if it goes beyond that, then it goes beyond repair, and then you have to put them back together into the right orientation. So each joint in the body therefore to some extent can exhibit all the mentioned movements within some limitations. Beyond a certain range, if such movements happen, they would lead to permanent damage or set, and then you have to really repair it through it's no longer repairable through chiropractic means, but you have to actually go ahead and do surgical techniques in order to put things back into place. So that is how I would record all the sort of motions related to the joints. Let us now study a little more about joint functions, that how joints would typically function. So the physiologic movement at joints mostly take place when muscles contract or when gravity acts on the bones to move it. You have to understand, so there is a sort of a knitted structure of the muscles and the bones, and so if supposing the muscles produce enough forces to lift a bone in the upwardly manner with respect to another, so there is some gliding across the bone to bone interface, but mostly the locomotor there is the muscle which is giving all the force. Okay, so the relative motion or movement of the bony joint partners relative to each other are typically referred as the osteokinematic movement, and the specific movements occurring in the articulating joint surfaces because of such motions. So relative motions, for example, let us say between the upper arm and the lower arm, is both these bones moving with respect to each other, so this, let us say for example this point is moving with respect to somewhere here in a certain coordinate frame in a certain manner. But if I looked at what is happening across this joint, typically there is some sliding action which is happening and some rotation or a rolling which is happening between two different members which are now being integrated with a musculostructure which is around it. Okay, so arthrokinetic movement is related to what is happening locally at the joint vis-a-vis the osteokinematic movement, which is relative to what the gross bone 1 is moving with respect to the bone 2. So it is necessary that both the osteokinematic as well as the arthrokinematic movements be considered together in unison when you are trying to model how biomechanistically different members are moving with respect to one another. So if I looked at a joint and tried to figure out what is the mechanical axis of a joint, this will typically be a line passing through the moving bone oriented perpendicular to the center of the stationary joint. For example, so typically you can see that this joint, it's a rotational motion which is being executed here in form of a spin across this particular axis, which is actually the mechanical axis around which the joint exists. So obviously if I look more into the detail of how a joint would move relative to each other when we consider the arthrokinematic aspect, so there is of course a some kind of a convexity and concavity across which there is a relative motion. So I like to end this lecture here in the interest of time, but in the next lecture I will take this up, that how there is rolling between the concave and convex surfaces in such joints, and then how there are lateral motions, and are there any specific relations that we need to obey when we talk about concavity moving over a convexity or vice versa. and then we will try to sort of look into how ergonomically we can design different postures which are going to be beneficial for the human body if prolonged for a certain amount of time, okay, without damaging the musculoskeletal system consistently. So, with this I will end this lecture. Thank you very much.